So next we're going to talk about what Dijkstra's algorithm is. So previously we talked about what the single source shortest path problem is. Now we're going to talk about an algorithm for computing shortest ST paths. Specifically, to solve the single source shortest path problem, it is to compute a shortest path tree of the source S. I just want to mention a couple of quick things. So first, if you're wondering why it's called Dijkstra's algorithm, this is named after the computer science pioneer Dijkstra, who developed this in the late 1950s. So before we get into the nitty-gritty of this thing, I thought I would give you a couple of motivating ideas for how we're going to come up with this algorithm. So there's kind of two ideas. That we've previously seen before that I want to bring together. So the first one is that for unweighted graphs, we know how to compute shortest paths, right? Because remember, that's just a special case of our problem. If I wanted to compute a shortest path tree, it would just be one where the edge weights are all the exact same. And in that case, I could use breadth first search, right? So we know how to compute shortest path trees on unweighted graphs using breadth first search. So we know how to do that, right? Likewise, previously we've also seen how we can compute minimum spanning trees. That had also a mechanism for producing a spanning tree. The shortest path tree is a spanning tree, just to be very clear, because our graph is connected. So there's going to be an element of Prim's algorithm that we've seen earlier. We're going to try to generalize that concept so that instead of it being about trying to compute the least weight cost of the spanning tree, I want to make it so it's as small as possible. Instead, I'm going to change it. I'm going to change it or augment it or generalize it, whichever one is your pleasure. I'm going to make it so that instead of it being about measuring the total cost over the entire graph, meaning that it's just the least weight edge, right? That's what I did with Prim's algorithm. Instead, I'm going to make it so it keeps track of how far away from the source we are. So we're going to take an idea. So I'm going to say perhaps let's take an idea from how we computed MSTs, so minimum spanning trees, to account for distance from S, the source. So this is going to be something we're going to call an edge relaxation. So you're going to look at this and be like, that reminds me a lot of the thing you do in Prim's algorithm, except we're instead going to account for not just like the cost, the weight of that edge. Now I want to take into account the distance I am for my vertex from S. I would like to keep track of the shortest distance so far. Let's think of it as an estimate if you would prefer. So that's going to be the purpose of what we call an edge relaxation. So we're going to keep track of a so far shortest distance from S to each vertex V we're going to call that v.d. Now you might recall I used the same name for when I talk about Prim's algorithm. It's going to have the exact same setup as I did in Prim's algorithm, except it's going to be that it's going to keep track of the so far shortest distance, not the cost of the least weight edge that we use, as I mentioned. This is going to translate very naturally into a very simple modification to from what we had for Prim's algorithm. So consider an edge. So consider an edge E, where it's going to have its endpoints being U and V. Where U is the vertex. Is the vertex that most recently joins the blob. Joins the blob B. And V is not in the blob. So to update the distance is to relax the edge. So to update the distance, what you do is you relax the edge UV. So that's what we'll refer to it as. So if we find a shorter distance, we relax the edge as follows. So it must satisfy the following condition. So I'll remind you a little bit of something. So if u.d plus the weight from u to v, so this edge, is less than currently the best distance we have for vertex v to from S, then we're going to relax the edge. So relaxing the edge is simply where we update d for v, such that it's just going to be u.d plus the weight of this new edge that I've encountered. So that's what an edge relaxation is. If you're not sure about what we're looking at here, just keep in mind this is just like the one we've seen in Prim, just now we're taking into account the distance from S to this vertex V. I want to see, do I currently have the shortest distance to V from S? So to do this, I have to account for the distance that I took to get there. So what is this all going to translate into? So now I know how to compute a spanning tree using Prim's algorithm. What I could do is try to adapt this idea of an edge relaxation as follows. So do you remember that I told you when we computed a minimum spanning tree, what happened was we had a blob and it would start at some vertex. In our setting, it's going to be S, the source. And this blob is always going to, it's attempting to devour the entire graph. So it goes vertex to vertex, picking some edge. In the case of Prim's algorithm, it always picks the least weight edge from inside the blob to outside the blob, and then it extends off to that next vertex and devours that vertex, making the blob larger, so growing the blob. And at the end of this process, what's inside the blob is a minimum spanning tree in that case. What happens here in contrast is I have a blob, but it's not just a blob that's going to follow that kind of rule. The same idea is going to be here, except it's even simpler. The blob is lazy. This blob is lazy this time around. As opposed to in Prim, it's just going to gobble up whatever's closest to the blob. That's a very proactive blob. The one we're going to be considering this time is a very lazy. This blob is going to be lazy. It's going to, imagine it starts off at vertex S at the source. And what it's going to do is it's always going to pick the vertex that is closest to the source. So that means that this blob is really, really lazy. So what it's going to imagine is you're going to imagine this blob is going to be sitting here being like getting bigger and bigger as it devours parts of the graph. And what's going to happen is you're going to imagine this blob is sitting there, and you imagine each one of our vertices is hanging almost away from the blob, and the blob is always going to find the one that's closest to its, we can imagine the source is where its mouth is, if it had a mouth. Yeah, don't get too imaginative with this. And what it does is it pulls in to the source, the next vertex that is closest to it. So it brings it in. Whichever one is the closest is the next one closest to the blob's mouth, right? So it's going to get closer and closer, and it will grab whichever one is the closest. So unlike in Prim's algorithm where the blob just goes for the one that's closest to the blob, it's just going to go for the one that's always closest to its mouth at the source. It's a lazy blob. It doesn't want to just travel to the one that's closest to the entirety of the blob. It requires it to be the one that's closest to its mouth, okay? And that's going to be the idea behind Dijkstra's algorithm. So again, it is a greedy algorithm, just like Prim's algorithm was. But here's the idea. The blob in Dijkstra's algorithm. Now, if you don't like me talking about it as a blob, it's just a set of vertices. So these are the ones that are going to be leaving the priority queue that we had in Prim's. So in Dijkstra's algorithm, our blob is always going to devour the next, it's always going to get the one that's the next closest to the blob's origin, which is the source. So now that we have all these bits and pieces, let's put Dijkstra's algorithm together. And here's the catch. Here's the catch. It's just going to look like I wrote down Prim's algorithm, where instead of having it where we have the updates of the least weight edges, as we had before, we've just changed this one bit about how the blob picks the next closest vertex. It always picks the one that's literally closest to the source. So it has to go from inside the blob to outside the blob again, but it's always going to be picking a vertex that is closest to the source, the origin of the blob, where its mouth is. So we've got our algorithm. So we're going to call it Dijkstra. It's going to have the graph G, and it's going to be given the source S. So as input, it's going to be a connected, undirected, weighted graph. G is equal to VE, and a vertex or source, however you'd like to call it, S, which is going to be one of the vertices. And as output, now I'm not going to return anything in our version of Dijkstra here, but you can easily make it so it returns all sorts of different things. I'm just going to make it so it constructs the shortest path tree. So it's going to produce the shortest paths from S to all vertices. So this is the shortest path tree rooted at S, right? So I promised you I was going to show you how you actually construct this, and this algorithm is what we're going to use to say that. So you're going to see that the setup for this is just like Prim's algorithm. I showed you how to represent Prim's using a priority queue. You're going to use the same setup. So you're going to first do some little bit of prep on the graph. So you're going to assign each one of the D values for each vertex to be not 0, it's infinity, right? Because we haven't yet encountered all of them yet. We have to, and the blob has to find them first. And then each one of its parents or predecessors are going to be null. We haven't found them yet either. So we start off by assigning the D value of the source to be 0, right? Because it's the shortest distance the distance from S to itself is 0, right? There's nothing too mind-blowing about that. Then next, we're going to make the priority queue. We're going to call it Q. It's going to contain all the vertices. All vertices V in V, where V dot D, well, where each V dot D is the key of an entry, right? So this is something we've established earlier with Prim's algorithm. We're going to have it where the D values are going to be the keys that we're going to use to maintain the priority queue in our heap-based implementation here. Because remember, we always want to get the one with the smallest D value. That's true regardless of Prim or Dijkstra's algorithm. So it's always the one with the smallest D value. We're just updating the D value a little different here. So now we just have our loop. We're just going to go through and keep repeatedly taking out vertices and giving them over to the blob to devour them, or the vertex joins the blob. While Q is not empty, we're going to do the following. We're going to pick out U min, which is going to be the one that is closest to the blob's mouth next. We're going to go remove min. We're going to apply remove min on the priority queue. We're going to pull U min into the blob. Because remember, as we do this, every single time, it's going to leave the priority queue. We're never going to put vertices back into the priority queue. We're going to potentially update their keys, but most certainly we're not going to put them back in once they get out. So each one's going to get their turn. That's something to keep in mind. So upon doing this, you can mark each one of them. I'm not going to include that line, but you most certainly could put it in there optionally if you want to make sure each one of the vertices gets marked. It's not required at this stage because we could ensure that we're never going to put back U min. U min's not going back in. But for each, we have to go through the incident edges. For each edge, U min V. So we're going to go through all the incident edges on U min. We're going to potentially have to do an edge relaxation. Well, specifically, we're going to have to relax some edges potentially. So if U min dot D plus the weight of U min V is strictly less than V dot D, what am I supposed to do then? I relax the edge. Then I'm going to update V dot D to be U min dot D plus the weight of the edge to get to V from U min. Now, remember, this is where we're going to update the key by decreasing it, because we found a shorter way to get to V from S. We're going to decrease the key for V. It's going to be decreased down to V dot D because I just updated it. Then I'm going to update the predecessor or parent in the shortest path tree. V dot parent is going to be updated to U min. That closes this. That closes the loop. And then we'll close the while loop. So we go lose our for loop, while loop, and that's Dijkstra. That's Dijkstra's algorithm right there. Pretty fascinating stuff, right? So you might ask, Dan, what is the time complexity of Dijkstra? Now, there's the short answer and then there's the long answer. The long answer is that you just have to go look back at how we did things with Prim's algorithm. Because do you see that there's anything different other than we just changed a few lines in here, right? We just changed how remember the edge relaxation is like a generalization where we focus on the distances, right? Everything else about the algorithm is exactly the same as prims. But you notice that all these changes, they don't affect the overall time complexity, right? So the time complexity is the exact same as we had from prims. So just to be clear, we established earlier that if I use an adjacency list, and a binary heap, we could show that this algorithm runs in big O of m log n as G is connected. Note that you can easily pick up the other representation of Prim's algorithm, do the same little tweak to it, and you can end up with big O of n squared for the time complexity in that situation. Likewise, again, if you want to update or upgrade your priority queue so that the heap being used is instead of Fibonacci heap, you can improve the overall time complexity again, like we had before. So that's Dijkstra's algorithm. Pretty fascinating stuff. Let's do an example just to make sure we're clear about it. So anyways, we have our example. And when we initially set it up, when s is 4, we make the d value as we have right here, 0. And now remember, all the vertices are in this priority queue. So it pulls out the first vertex with the smallest d value. In this case, that would be s, right? That would be s. So it means that 4 comes out of the priority queue. But what does that mean? It means our friend the blob devours this vertex, right? That's where it starts off. So the blob says, hey, I'm going to eat this, and its orifice is going to be right here, okay? So it's going to be at 4. So remember, 4 is s. So remember, we're always going to find the vertex that is closest to s that's outside the blob. And that's what it's going to devour next. So we've done that. Now we got to go through all of our incident edges on 4. So we got to check this edge and this edge. So we see that, hey, look, if I take 0 plus the weight of this edge, which is 1, that is less than infinity. So I can update this. So I'm going to relax on this edge. So this is 1. And the parent needs to be updated. It's updated to 4. Same thing here. I found a shorter way to get the vertex 3 via this edge. And that's all my incident edges. So that finishes up dealing with vertex 4. So far, are we doing okay? Now next, the blob is going to find the next closest vertex to the blob's mouth. Remember, it's really lazy. It's going to drag that vertex, the one with the smallest d value, to its mouth and devour it, okay? So it's just, I'm just going to sit here. You're going to bring the one that's closest to me by my mouth. You're going to bring that to me. So that case would be vertex 1, right? So how do I know which one is an edge that's going to be the one that would be the one that I extend from vertex 4 to vertex 1? So which edge do I add in to the shortest path tree? It's this one, right? It's always umin and then its predecessor, right? So immediately once you've removed umin, you know which edge goes into this shortest path tree. It's right here. So if you had an auxiliary data structure where you wanted to add them in explicitly, you do it right here before this loop. So now the blob will devour vertex 1. And we go through all the incident edges on vertex 1. So notice here that I have a 3. So notice that the distance from S to 2 would be, in this case, 1 plus 3, because remember, that's what the d value is here. giving me a 4. And the parent in this case would be 1, right? Because that's the predecessor. That's how I would get to 2. Now notice that I have a distance of 2 here versus a distance of 1 plus 3, which is larger than 2, so we wouldn't relax this edge. We relaxed on this edge, but not this one. Do you see that? Notice that because this was the one with the smallest d value at that time, notice that I wouldn't relax this edge again, right? So notice that I have, it would be 1 plus 1, which is larger than, it's going to be larger than this one because this is the small, it would have been either the same or smaller, right? Before that. Why? Because it was closer to the mouth of the blob, right? So that completes that next iteration of this while loop. So next we're going to figure out the next closest vertex to the blob's mouth. Remember, the blob is just bridge in my mouth, okay? Put it in my mouth. So it gets the one that's closest. So notice I have a 2 versus a 4 versus an infinity. So I picked the one with the 2. So to get there is this edge, right? That's the predecessor. So 4 is the predecessor or parent of vertex 3. And the blob will devour vertex. And then it goes on all the incident edges and say, hey, look, let's see, 2 plus 2 is 4. That's bigger than 0. 2 plus 3 is 5. That's bigger than 1, right? You notice those ones, it doesn't make much of a difference, really. Well, it doesn't make any difference, right? Then we have, because remember, they're already in the blob, so it means that their d values had to have been either the same or smaller. So that's something I really want you to pay attention to. So versus 2 plus 4 is 6. That is less than infinity. So I'm going to update this. The d value of 5 to be 6 and its parent to be 3. And we've now considered all the incident edges, right? So next, let's go through and figure out which vertex goes in the blob's mouth. It's going to be the one that's closest, which is vertex 2, right? So to get to the orifice of the mouth, it's through this edge here, right? Because that's the parent of 2 is 1. So the blob devours vertex 2. And then at last, we check all the incident edges. So notice that I have 4 plus 3 is 7. That's bigger than 1. Don't do anything with that. And then next we have 1 plus 4 is 5. That's less than 6. So I'm going to update this. So I'm going to relax this edge. This one right here. Its parent's going to be updated to 2. And next, of course, we are going to pick our next one, right? So let's pick the last one here. So notice that I could just use this edge here because notice that the d value for 5, that's the last one we have left. There's the only one we have left. So by default, you would pick this one. You take that one, the blob devours this, and it has devoured the entire graph. And of course, you could go through all the incident edges again, perform relaxations, but you'll notice that none of them would get updated because, of course, it's 1. It would be 5 plus 1 is 6. That's larger than that. 5 plus 4 is 9. That's bigger than 2, right? So notice that you wouldn't relax these edges. That's the thing I'm really getting at. But yeah, here's an example execution. The shortest path tree is, in fact, indicated with the red edges here. So as a little exercise, I encourage you to try picking another source and seeing if you get a different shortest path tree, or just simply try, just try another set of vertices. Just try another one. Just try a couple just to see if you can convince yourself that you understand this algorithm. But yeah, that's Dijkstra.